Right now, as you
Observe the
hear
red
these
spike here.
words,
It's a
you are
critical threshold
spinning.
breach.
Not
Correlate this with the
metaphorically,
green
not
metrics for
poetically,
confirmation.
actually spinning 1,000 miles per hour. That's how fast the ground beneath your feet moves as Earth rotates.
The
Faster than a
patterns are
bullet
converging.
train,
Something's happening.
faster than the speed
I
of
need to get a
sound.
closer look.
You don't feel it because everything
The readings are
around you,
spiking.
the
It's
air, the
destabilizing.
trees, the
I need to
buildings, your
reroute the
coffee
containment
cup,
field.
everything is
Now!
spinning with you. For your
Global data
entire
shows
life,
anomalies
this
in
has
these
been
regions. We
constant,
must analyze the
reliable.
patterns
The
immediately.
sunrises,
The implications
the
are
sunsets.
significant.
24 hours, day after day after day, except on June 29th, 2022, something strange happened. Earth completed one full rotation 1.59 milliseconds faster than it should have. The shortest day in 50 years, not by hours, not by minutes, by milliseconds, thousandths of a second, an amount of time so small you couldn't possibly notice it. Your heart beats once every 800 milliseconds. A blink of your eye takes 300. This change invisible to human perception. But not to the machines. Deep in a basement laboratory in Boulder, Colorado, sits a device that has been counting time since 1955. Not with gears or springs or pendulums. With atoms. Cesium-133 atoms to be precise. 9,192,631,770 vibrations of these atoms equals exactly 1 second. Not approximately. Exactly. This atomic clock is so accurate it wouldn't lose a single second in 300 million years. If you had somehow turned it on when the first dinosaurs walked the Earth, it would still be accurate to within a few seconds today. And this clock noticed. It flagged an anomaly, a discrepancy between the time it measured and the time Earth's rotation should have given. The planet had finished its spin too early, just barely, but measurably. And then it happened again, and again. Throughout 2020, 2020, 2020, 2020, 2020, 2020, 2020, 2020, 2020, 2020, 2020, 2020, 2020, 2020, Day after day, becoming fractionally impossibly shorter. Now you might think, so what, a millisecond here or there, who cares? But here's the thing about precision. When you can measure something down to the billionth of a second, when you can track a planet's rotation with that kind of accuracy, tiny changes stop being trivial. They become clues. Clues that something fundamental has shifted. Because Earth has been spinning for 4.5 billion years, steadily slowing down for most of that time like a top gradually losing momentum. The moon's gravity pulls on our oceans, creating tides that act like brakes, stealing a tiny bit of rotational energy with every passing day. This has been happening for eons. Measurable, predictable, so predictable that scientists have been adding leap seconds to our clocks since 1972, 27 of them, in fact, to keep our human-made time synchronized with the planet's gradually slowing spin. But in 2020, for the first time in recorded history, that trend reversed. Earth started speeding up, and nobody knows why. To understand how strange this is, you need to understand how we know what we know about time itself. For most of human history, time was simple. The sun came up, the sun went down. One day, people divided this day into 24 hours, an arbitrary choice made by ancient Babylonians and Egyptians who liked the number 12 and decided to use it twice. It worked well enough for millennia. Sundials, water clocks, eventually mechanical clocks with gears and springs. Each generation's clocks got a little more accurate, but they were all based on the same fundamental assumption: Earth rotates at a constant speed, giving us days of equal length. Then in the early 20th century, scientists developed clocks accurate enough to notice something unsettling. Earth's rotation isn't constant. It wobbles. It speeds up and slows down in irregular patterns. Some days are longer than others by tiny fractions of a second. This created a problem. If Earth doesn't turn at a perfectly steady rate, how do you define a second? For a while, astronomers tried to create an averaged second based on Earth's mean rotation. But this was like trying to use a drunk person's walking pace as a standard measurement of speed. It worked sort of, but it wasn't precise. Then came Louis Essen. In 1955, at the National Physical Laboratory in England, Essen built something revolutionary. Instead of measuring time by watching the heavens or counting the swings of a pendulum, he measured it by watching atoms. Cesium-133 specifically. When you heat cesium atoms and expose them to microwave radiation at just the right frequency, something remarkable happens. The atoms vibrate, oscillate between two energy states with perfect, unwavering regularity. No matter the temperature, no matter the pressure, no matter what's happening in the world around them, cesium atoms vibrate at exactly the same frequency: 9,192,631,770 times per second. Essen counted these vibrations and used them to define the second. Not based on Earth's rotation, not based on anything astronomical, based purely on the fundamental behavior of matter itself. In 1967, the scientific world agreed. The second was redefined, no longer 1/86,400th of a mean solar day. Now officially the duration of 9,192,631,770 periods of radiation corresponding to the transition between two hyperfine levels of the ground state of the cesium-133 atom. A mouthful, but precise beyond anything humans had ever achieved. This level of precision revealed something that had been invisible before. Earth is a terrible clock. Its rotation speed changes constantly. Atmospheric pressure systems shifting around the globe can speed it up or slow it down by fractions of milliseconds. Earthquakes redistribute mass, changing the planet's moment of inertia, making it spin slightly faster or slower. Melting ice at the poles sends water flowing toward the equator, redistributing mass and affecting rotation. And then there's the moon. Every day, the moon's gravity pulls on Earth's oceans, creating bulges of water, high tides on the side facing the moon and the side opposite. But Earth rotates faster than the moon orbits, so these tidal bulges don't stay perfectly aligned with the moon. They get dragged ahead by Earth's rotation. The moon pulls back on these misaligned bulges. It's like grabbing a spinning wheel from the side. Friction. Drag. The moon's gravity acts as a brake, constantly stealing rotational energy from Earth. This energy doesn't disappear. It transfers to the moon, slowly pushing it into a higher orbit. Laser reflectors left on the lunar surface by Apollo astronauts allow scientists to measure this. The moon moves approximately 1.5 inches farther away from Earth every year. And as the moon drifts away, Earth's rotation slows. Not fast, unimaginably slowly. Over the course of a century, the day gets longer by about 1.7 milliseconds. Over millions of years, this adds up. When the first primitive life appeared on Earth, a day was only about 16 hours long. The moon was much closer. The tides were enormous, and everything spun faster. Since 1972, when atomic clocks became precise enough to track these changes in real time, scientists have been compensating for this slowdown by adding leap seconds to our calendars. Usually at midnight on December 31st or June 30th, clocks around the world would read 11:59:59, then 11:59:60, then 000000. An extra second inserted to keep atomic time synchronized with Earth's slowing rotation. 27 leap seconds added in 50 years. All because Earth was gradually, predictably slowing down. Until 2020. The change didn't announce itself dramatically. No earthquakes, no solar flares, no obvious catastrophe, just data. Scientists monitoring Earth's orientation parameters, measurements of exactly how the planet is positioned in space, how fast it's rotating, how its axis is tilted, started noticing something odd in their spreadsheets. The numbers weren't behaving as expected. Instead of days getting gradually longer, requiring periodic leap seconds to compensate, days were getting shorter. At first, the anomalies were small, well within the range of normal variation. Earth's rotation speed fluctuates all the time due to atmospheric changes, ocean currents, seismic activity. But as months passed, a pattern emerged. The fluctuations weren't random. They were trending in one direction, faster. In 2020, Earth experienced some of the shortest days on record. Then 2021 went further. By 2022, the planet was breaking its own records regularly. And then came June 29th, 2022. On that day, Earth completed one full rotation, one complete spin on its axis in 86,399. 998,410 seconds. Standard day length, 86,400 seconds. Difference, 1.59 milliseconds. The shortest day in 50 years of precision atomic timekeeping. For the first time since scientists began adding leap seconds in 1972, they began seriously discussing removing one instead. A negative leap second, turning the clock backward by 1 second to compensate for the planet spinning too fast. This had never been done. Not once, not in all of human history, and the prospect terrified engineers. Every leap second ever added has caused problems. Software systems not designed to handle a 61st second in a minute have crashed. In 2012, Reddit, Mozilla, and several major airlines experienced outages when servers couldn't process 11:59:60. In 2017, Cloudflare, a company that routes traffic for millions of websites, suffered a massive failure during a leap-second event. Adding a second is hard enough. Removing one, jumping backward in time. Most software has never been tested for that scenario. Nobody knows what would break. GPS satellites, which depend on nanosecond-level timing, precision could glitch. Financial trading systems that timestamp transactions to prevent fraud could malfunction. Power grids synchronized across continents could desynchronize. But beyond the technical concerns, beyond the engineering headaches, the negative leap second represented something more profound. A question. After 4.5 billion years of gradually slowing down, after 50 years of reliable, predictable deceleration, requiring periodic corrections to our clocks, why was Earth suddenly speeding up? What had changed? The answer, as it turns out, is not simple, because Earth is not a simple machine. It's a system, a vast, interconnected system of moving parts, each influencing the others in ways that can be subtle, powerful, and maddeningly difficult to disentangle. Think about what Earth actually is. At the very center, about 4,000 miles beneath your feet, there's a solid ball of iron and nickel. This inner core is roughly the size of the moon, subjected to pressures so extreme that despite temperatures exceeding 9,000 degrees Fahrenheit, as hot as the surface of the sun, the metal remains solid, crushed into crystalline form by the weight of the entire planet pressing inward. Surrounding this inner core is the outer core. 2,000 miles of liquid iron and nickel churning and flowing in massive convection currents. This molten metal moves, and as it moves, it generates something crucial: Earth's magnetic field, the protective bubble that shields us from solar radiation and cosmic rays. But the outer core doesn't rotate at exactly the same speed as the solid Earth above it. It can't. It's liquid. It can slip and slide relative to the mantle, the thick layer of hot, slowly flowing rock that makes up most of Earth's interior volume. Above the mantle lies the crust, the thin, cool, brittle shell we live on. Continental plates drifting across the surface, colliding, subducting, mountains rising and eroding. Covering much of this crust, oceans, massive bodies of water totaling about 1.4 billion cubic kilometers that slosh and flow in currents driven by wind, temperature differences, and the Coriolis effect created by Earth's rotation. And surrounding everything, the atmosphere. 5 quadrillion tons of air organized into pressure systems and wind patterns that circle the globe, carrying heat from the equator toward the poles, moisture from the oceans over the continents, energy that manifests as weather. Finally, at the poles and on high mountains, ice. Trillions of tons of frozen water sitting on land, pressing down on the crust, reflecting sunlight back into space. Each of these components, core, mantle, crust, ocean, atmosphere, ice, is in motion. Each affects the others, and together their collective motion determines how fast Earth spins. Change one component and everything responds. This is not a simple cause and effect relationship. It's a web of interactions. A conversation happening between different parts of the planet, conducted over timescales ranging from seconds to millions of years. And right now, something in that conversation has changed. To understand what we need to listen to the people who have spent their lives learning to hear it. Scientists who have dedicated decades to measuring forces that are invisible, enormous, and operating miles beneath the surface or thousands of feet above our heads. We need to go deeper. Literally, 2,000 miles down into the churning heart of the planet, where something is happening that nobody predicted. Dr. John Vidali doesn't look like someone who spends his time thinking about the center of the Earth. At 67, with wire-rimmed glasses and a perpetual expression of mild skepticism, he could be a retired accountant or a philosophy professor. Soft-spoken, careful with his words, the kind of person who pauses before answering questions, as if checking his internal calculations one more time before committing to a statement. But for 40 years, Vidali has been a seismologist at the University of Southern California, a forensic detective of Earth's interior, using earthquake waves the way a doctor uses X-rays to see inside a patient's body. And in 2023, he published a paper that made geophysicists around the world stop and recalculate. Earth's inner core, he announced, had changed its rotation, not slightly, not ambiguously, measurably, significantly changed. To understand why this matters, you need to understand what seismic waves are and what they reveal. When an earthquake occurs, it sends vibrations, waves of energy radiating through the entire planet. Some of these waves travel along the surface, causing the shaking we feel. But others dive deep, passing through the mantle, through the liquid outer core, and even through the solid inner core. Different types of rock, different phases of matter, different temperatures and pressures, all of these affect how fast seismic waves travel and how they bend and reflect. By placing seismometers around the world and carefully measuring when earthquake waves arrive at each station, scientists can create a kind of sonogram of Earth's interior. They can see things no human eye will ever directly observe. Vidali specializes in a particular type of analysis. He looks at earthquake doublets, pairs of earthquakes that occur in almost exactly the same location, sometimes years or decades apart. Same place, same fault line, same type of rupture. When two earthquakes happen at nearly identical locations, they should send out nearly identical seismic waves. Except sometimes they don't. Sometimes waves from the second earthquake arrive at distant seismometers slightly faster or slower than waves from the first earthquake did. The difference is minuscule fractions of a second over thousands of miles, but it's real. And the only explanation is that something along the path the waves traveled has changed, specifically the inner core. For years, geophysicists have known that Earth's inner core rotates slightly faster than the rest of the planet. Not much faster, maybe a fraction of a degree per year, but measurably faster. This phenomenon called superrotation occurs because the inner core is partially decoupled from the mantle above it. It's surrounded by liquid metal. It can slip and slide spinning at its own pace. But Vidali's analysis of earthquake doublets from 1991 to 2023 revealed something nobody expected. The inner core's superrotation had slowed down dramatically. In fact, some of his data suggested the inner core might have stopped superrotating altogether. It might now be spinning at the same rate as the mantle and surface. Some interpretations of the data even suggested it might be rotating slightly slower, moving backward relative to the ground above. When Vidal presented these findings, they were controversial. Other seismologists pushed back, questioning the methods, the assumptions, the interpretations. This is how science works. Claims get challenged, data gets scrutinized. But the core observation that seismic waves passing through the inner core were arriving at different times than they used to, that observation held up. Multiple independent research teams confirmed it using different earthquake data, different analytical methods. Something had changed in the deep interior. The inner core, that moon-sized ball of solid iron 4,000 miles beneath our feet, had altered its rotation relative to the surface we live on. And here's where it connects to our spinning planet. The inner core, the outer core, the mantle, and the crust don't all rotate as one locked system. They interact through friction, through magnetic forces, through gravitational coupling. When one layer changes its rotation speed, it exchanges angular momentum with the layers around it. Think of it like gears in a complex machine, except the gears are made of iron and rock. They're thousands of miles across, and they're connected not by teeth but by magnetism and gravity. If the inner core slows down, that rotational energy has to go somewhere. Some of it transfers to the outer core, some to the mantle, and eventually some reaches the surface, making the crust spin slightly faster. This process is called core-mantle coupling, and it's one of the forces, one of several, that affects Earth's rotation speed. But it's slow. Changes in the core propagate upward over years or decades, not days or weeks. So if core-mantle coupling is part of what's speeding up Earth's rotation right now, it means something shifted in the deep interior. Years ago, something that's only now showing up in our measurements of day length. We can see the effect, Vidali says, but we still don't fully understand the cause. He has theories. Some researchers think it's part of a natural cycle, a roughly 60 to 70-year oscillation, where the inner core alternates between superrotating and subrotating. If that's true, we might be entering a phase that will last for decades, gradually transferring angular momentum from the core to the surface, keeping days shorter than they used to be. Others think it might be related to changes in the outer core's flow patterns. The liquid iron churning around the inner core generates the magnetic field, and that field has been weakening in some regions, intensifying in others. These changes could alter the magnetic coupling between the inner and outer core, changing how they interact mechanically. The honest answer is we don't know for certain. What we do know is that something fundamental shifted in the planet's interior. A force operating thousands of miles below ground, invisible, unreachable by any drill ever built, is nudging the rotation speed of every living day on the surface. It's one piece of the puzzle, but only one. Because while Vidale was studying earthquake waves traveling through the core, other scientists were looking elsewhere. Up, not down, at the ice sheets sitting at the very top and bottom of the world. And what they found there made the rotation mystery even stranger. The mathematics of rotation are beautifully simple. If you've ever watched a figure skater spin, you've seen this principle in action. Arms stretched out wide, the skater rotates slowly. Then pull the arms in tight against the body, and suddenly they're spinning faster. Much faster. No additional push needed, just a change in how mass is distributed relative to the rotation axis. This is conservation of angular momentum. It's one of the fundamental laws of physics. The amount of rotational energy in a closed system stays constant unless an external force acts on it. But how that energy manifests, how fast something spins, depends on how the mass is arranged. Move mass closer to the axis of rotation, spin faster. Move mass farther away, spin slower. Earth is a rotating system, and mass on Earth is constantly being redistributed. Water evaporates from the ocean and falls as snow on Greenland, accumulating in ice sheets. Then as climate warms, that ice melts and flows back into the ocean. Entire rivers change their courses. Aquifers are pumped dry. Reservoirs are built, holding back trillions of gallons of water in artificial lakes. Every time mass moves from one location to another, Earth's moment of inertia changes, even slightly. And when the moment of inertia changes, so does the rotation speed. This is where Dr. Duncan Agnew enters the story. At 73, Agnew has spent the majority of his career at Scripps Institution of Oceanography, studying something most people have never heard of: the Chandler wobble. It sounds like a dance move. It's actually a tiny irregular oscillation in Earth's rotation axis, a wobble, that causes the geographic North Pole to trace a small circle about 30 feet in diameter, roughly every 14 months. 30 feet, on a planet 8,000 miles across. You need extraordinarily precise instruments to detect it, but Agnew has those instruments. And for 40 years, he's been tracking this wobble, trying to understand what causes it, what affects it, and what it reveals about the forces acting on our planet. His colleagues call him the wobble whisperer. He's measured variations so small they'd be invisible to any instrument built before the 1980s. He's documented how earthquakes nudge the wobble, how ocean currents affect it, how atmospheric pressure changes show up in the data. And in recent years, Agnew noticed something that connected directly to Earth's changing rotation speed. The ice sheets are melting fast. This isn't speculation or projection. It's measured reality. Satellites equipped with instruments called gravimeters, devices that detect tiny changes in Earth's gravitational field, have been mapping exactly where mass is increasing and where it's decreasing across the planet's surface. The data is unambiguous. Greenland is losing approximately 280 billion tons of ice per year. To put that in perspective, if you could somehow stack that much ice into a single block, it would cover the entire state of Delaware to a height of over 400 feet. Every year, flowing from the ice sheet into the ocean, Antarctica, both the West Antarctic ice sheet and the more stable East Antarctic ice sheet, is losing ice too. Not as fast as Greenland in most regions, but the total volume is staggering. And here's where it gets strange. When ice sits on land at the poles at the very top and bottom of Earth, right along the rotation axis, its mass concentrated as close to the axis as possible, like the figure skater with arms pulled in tight. When that ice melts and flows into the ocean, the water redistributes. It spreads out across the globe, raising sea levels everywhere, but particularly accumulating toward the equator, where Earth's surface is moving fastest and centrifugal force is greatest. Mass moving away from the poles, away from the rotation axis, out toward the equator, like the skater throwing their arms wide. This should slow Earth's rotation. According to every model, every calculation, every basic principle of physics, melting polar ice should be making days longer, not shorter. And yet, days are getting shorter. Agnew spent months double-checking the calculations. The mass loss from ice sheets is well documented by multiple independent satellite missions. The redistribution of that mass is exactly what models predict. The effect on rotation should be clear, but the actual measured rotation speed is going in the opposite direction. It's a paradox, Agnew says. The ice is doing what it should do. The physics is correct. But something else, some other force or combination of forces is overpowering it, which means something else is not only speeding up Earth's rotation, but doing so with enough strength to overcome the slowing effect of billions of tons of melting ice. What could possibly be strong enough to do that? The answer lies in something most people never think about: the air. If you stopped 100 people on the street and asked them how much the atmosphere weighs, most would say it weighs nothing. Air is light, ephemeral, almost not there. This is spectacularly wrong. The atmosphere, all the gas surrounding Earth from sea level up to the edge of space, weighs approximately 5 quadrillion tons, 5,000 trillion tons. To put that in comprehensible terms, if you could somehow gather all the water in all the oceans and stack it up, the atmosphere would weigh about 1/300th as much. That sounds small until you realize oceans are unimaginably heavy. The atmosphere is heavy too. And it moves, not randomly, in enormous organized patterns. Jet streams, rivers of air flowing at hundreds of miles per hour at high altitudes circle the globe. Trade winds blow consistently across the tropics. Monsoon systems shift with the seasons, carrying moisture across continents. All of this moving air has momentum, angular momentum specifically. And when atmospheric circulation patterns change, when winds speed up or slow down, that momentum has to be conserved. It transfers to the solid planet beneath. Dr. Matthew Dumberry has spent 20 years studying this interaction. At 54, working from the University of Alberta in Canada, he's become one of the world's leading experts on atmospheric angular momentum. Transfer, the technical term for how the atmosphere's motion affects Earth's rotation. His research shows something remarkable. During a strong El Nino event, when ocean temperatures in the Pacific shift dramatically, reorganizing weather patterns across the entire planet, atmospheric circulation changes significantly. The jet streams shift position and speed. Trade winds weaken or strengthen. Massive pressure systems reorganize. When this happens, the length of a day changes by up to zero point 0.2 milliseconds. Not much, but measurable. And it happens relatively quickly over months, not years. The mechanism is straightforward. When wind patterns slow down, when the atmosphere's rotation relative to the surface decreases, that lost angular momentum transfers to the solid Earth. The ground speeds up to compensate. When winds accelerate, the opposite happens. Think of it like a dancer spinning while holding a long scarf, Dummery explains. When the scarf wraps tighter around the dancer, they spin faster. When it unfurls, they slow down. The dancer and scarf are coupled. Changes in one affect the other. His calculations show that changes in atmospheric circulation over the past few years could account for a significant fraction of the observed rotation acceleration. But there's a complication. The atmosphere itself is changing. Climate change is altering wind patterns. The jet streams are shifting latitude, becoming wavier, less stable. The temperature difference between the equator and the poles, the fundamental driver of atmospheric circulation, is shrinking because the Arctic is warming faster than anywhere else on the planet. When the system itself is changing, it becomes much harder to predict what it will do next. Dummery can measure what the atmosphere is doing right now. He can show that it's contributing to faster rotation. But whether this is a temporary fluctuation or the beginning of a longer-term trend, that's harder to say. And then there's the seasonal effect. Every year, like clockwork, the atmosphere expands and contracts with the seasons. In summer, in the northern hemisphere, where most of Earth's landmass is located, air warms and expands. The atmosphere becomes physically larger, pressing outward. In winter, it contracts. This breathing cycle actually changes Earth's rotation speed slightly with the seasons. Days in northern hemisphere winter are fractionally faster than days in summer. The difference is tiny, well under a millisecond, but it's there year after year, as regular as the orbit itself. You're living inside a system where the length of your day varies depending on the time of year. You can't feel it, but it's happening. All of this core changes. Ice melt, atmospheric circulation. These aren't separate phenomena. They're interconnected. The atmosphere responds to ocean temperatures. Ocean temperatures respond to ice melt. Ice melt responds to atmospheric heating. The core's magnetic field might influence atmospheric circulation through mechanisms we're only beginning to understand. It's a web, a planetary conversation. And somewhere in that conversation, the question remains, why after 4.5 billion years of mostly slowing down, is Earth spinning faster right now? The forces we've identified, core deceleration, ice redistribution, atmospheric momentum transfer, these are real. They're measured, they're understood at least partially. But when you add them all up, when you run the numbers through the most sophisticated models available, there's still a gap, a residual. Something in the data that the models don't fully explain, a signal that suggests there might be another force at work, or an interaction between known forces that we haven't properly characterized yet. This is where the complexity gets real, where the certainty gives way to honest scientific uncertainty. But there's context here that matters, a sense of scale that helps put all of this in perspective. Because Earth has been rotating for an unimaginably long time. And the story of how that rotation has changed over billions of years, that's a story written in rock, in fossils, in the ancient rhythms of tides that crashed on shores hundreds of millions of years before humans existed. And reading that story reveals something profound about where we are right now in Earth's long history. There's a particular kind of vertigo that comes from understanding scale, not the physical vertigo of heights or spinning. The intellectual vertigo of grasping just how vast time can be, how incomprehensibly long Earth has existed, how many days have passed since the planet first coalesced from cosmic dust. 4.5 billion years. If you counted one number per second, it would take you 142 years just to count to 4.5 billion. You'd need multiple human lifetimes just to speak the number of years Earth has existed. And in all that time, through the formation of continents, the rise and fall of mountain ranges, the evolution of life from single cells to the complexity of human consciousness, the planet has been spinning, day after day after day, but not always at the same speed. Dr. Linda Elkins Tanton sits in her office at Arizona State University, surrounded by rocks. Not decorative rocks, evidence. Samples collected from field sites around the world, each one a fragment of deep time, a piece of the puzzle that reveals Earth's history. At 62, she's a geologist who specializes in something most people never think about: planetary formation. How worlds are born, how they evolve, how they change over timescales that make human history look like a heartbeat. She picks up one particular specimen, a slice of banded iron formation polished to reveal layers of rust red and steel gray. Ancient seafloor sediment deposited 2.5 billion years ago, when Earth's oceans were rich in dissolved iron and the atmosphere contained almost no oxygen. This formed in a world so different from ours, it might as well be an alien planet, she says, turning the rock in the light. The sky was probably orange or pink. The oceans were green. There were no plants, no animals, nothing on land at all except rock and water. And the day was about 18 hours long. She sets the rock down carefully, precisely aligned with the edge of her desk. Everything in Elkins Tanton's workspace is precise, organized. The habit of someone who has spent decades working with fragmentary evidence, where every detail matters, where carelessness can lead to completely wrong conclusions. People have a hard time with deep time, she continues. They understand that Earth is old intellectually, but they don't really feel it. They can't. The numbers are too big. But there are ways to make deep time tangible, to translate billions of years into something the human mind can grasp. One method: look at what's changed. The moon provides a perfect measuring stick. Right now, at this moment, the moon is approximately 238,855 miles from Earth. That distance varies slightly as the moon follows its elliptical orbit, but on average, that's where it sits. 4 billion years ago, the moon was roughly 150,000 miles away. The difference, 88,855 miles. The moon has been drifting away at an average rate of about 1.5 inches per year. That seems impossibly slow. At that rate, it would take 63,360 years for the moon to move just 1 mile farther away. But Earth has had a lot of 3,600-year periods, approximately 71,000 of them, in fact. And during every single one, the moon has been stealing rotational energy from Earth through tidal friction, transferring it into orbital energy, and slowly, inexorably climbing into a higher orbit. The math is beautiful, Elkins Tanton says, pulling up a simulation on her computer. We can calculate exactly how much angular momentum Earth has lost, how much the moon has gained, and it all balances perfectly. Conservation laws hold. The numbers work. The simulation shows Earth and moon at various points in history. 4 billion years ago, the moon looming huge in the sky, tides hundreds of feet high, crashing across primordial continents. 3 billion years ago, slightly farther, tides diminished, but still enormous. 2 billion years ago, 1 billion. Each frame, the moon is smaller in the sky. Each frame, the tides are gentler. Each frame, the day is longer. What gets me, she says, is thinking about the organisms that live through these changes. Not individuals, obviously, but lineages. Species that existed for millions of years would have experienced measurably different day lengths over their evolutionary history. Life had to adapt. Circadian rhythms had to adjust. The fundamental biological clocks that tell organisms when to sleep, when to eat, when to reproduce, all of that evolved in a world where days were getting longer. She pauses, considering. We think of evolution adapting organisms to their environment. We think about temperature, salinity, oxygen levels, predators. But organisms were also adapting to time itself, to the changing rhythm of day and night. This is the context that makes the current rotation changes meaningful. Not because they're large in absolute terms, they're not. Even the record-breaking short day in 2022 was only 1.59 milliseconds faster than standard. But because they're happening in the opposite direction from billions of years of history, and they're happening fast, geological processes usually operate slowly, Elkins Tanton explains. Continental drift moves at the speed your fingernails grow. Mountain ranges rise over millions of years. Even relatively rapid events like the asteroid impact that ended the Cretaceous period, their effects play out over thousands of years. But Earth's rotation, that can change on human timescales. And right now, it is. The question is, why now? What's different about this particular moment in Earth's 5 billion year history that would cause rotation to accelerate after so long slowing down? Part of the answer lies in where we are in Earth's climate cycles. For the past 2.6 million years, Earth has been in an ice age. Not continuously frozen, the planet oscillates between glacial periods, when ice sheets advance across continents, and interglacial periods, when they retreat to the poles. But overall, compared to most of Earth's history, we're in a cold phase. These oscillations follow predictable patterns driven by variations in Earth's orbit and axial tilt. The Milankovitch cycles named after Serbian mathematician Milutin Milankovitch, who calculated them in the early 20th century. Earth's orbit isn't perfectly circular, it's slightly elliptical, and that ellipse becomes more or less pronounced over a cycle of about 100,000 years. Earth's axial tilt, the angle between its rotation axis and the plane of its orbit around the Sun, varies between about 22 degrees and 25 degrees over a cycle of 41,000 years. And Earth's axis wobbles like a spinning top, completing one full wobble roughly every 26,000 years. These cycles don't change the total amount of sunlight Earth receives, but they change how that sunlight is distributed. More summer sun in the northern hemisphere, where most land is located, melts ice. Less summer sun allows ice to accumulate. Over the past million years, these cycles have driven ice ages with remarkable regularity. About every 100,000 years, ice sheets advance, covering Canada, Scandinavia, parts of northern Asia. Sea levels drop by 300 feet or more as water gets locked up in ice. The coastlines shift. Land bridges appear between continents. Then over a period of 10,000 to 20,000 years, the ice melts. Sea levels rise. The climate warms. We're living in one of those warm periods right now, an interglacial. The ice retreated from North America and Europe about 12,000 years ago, leaving behind the Great Lakes, countless smaller lakes, and radically reshaped landscapes. But here's the crucial point: the ice didn't disappear completely. Greenland still has a massive ice sheet. Antarctica still has too. These remnants from the last glacial maximum are still here, still melting, slowly, still releasing water into the oceans. And that ongoing melt, sped up dramatically by human-caused climate change, is redistributing mass on a planetary scale. But the evidence of Earth's changing rotation doesn't just come from satellites and modern instruments. It comes from something far older, something written in stone. The past is written in layers. Sediment deposited in ancient shallow seas, one tidal cycle at a time, building up over thousands of years into rocks that geologists can read like books. These are called tidal rhythmites. When tides rise and fall twice daily following the moon's gravitational pull, they leave behind thin layers of sediment. Each layer represents one tidal cycle, like tree rings but for the ocean. Over time, these layers accumulate, recording not just daily cycles, but also the slower rhythm of spring tides and neap tides, the monthly variation caused by the sun and moon's combined gravitational effects. By counting the layers, by analyzing their thickness and spacing, geologists can determine how many tidal cycles occurred in a month, how many days occurred in a year. And what they find is extraordinary. Tidal rhythmites from roughly 620 million years ago, from a period called the Late Precambrian, show approximately 420 daily layers per annual cycle, 420 days in a year. Earth's orbit around the sun hasn't changed significantly in that time. A year is still a year, roughly the same length. But if there were 420 days in that year, instead of 365, each day must have been shorter. About 21 hours long, 21 hours, 3 hours shorter than today. Earth was spinning significantly faster. The moon was much closer, perhaps 20,000 miles closer than it is now. Tides were enormous. The day-night cycle was rapid, and life existed. Simple life, true. Mostly single-celled organisms, though some early multicellular organisms were beginning to appear. But they lived in a world fundamentally different from ours. A world where the sky moved faster. Fossils of ancient corals provide even more detail. Corals grow daily growth bands like trees, visible under magnification. They also have seasonal variations. Growth is faster in summer than winter. By counting daily bands within annual cycles in fossilized corals from different geological periods, scientists have traced Earth's rotation speed back through time. 400 million years ago, approximately 400 days per year. Days about 22 hours long. 200 million years ago, approximately 385 days per year. Days about 23 hours long. The trend is clear, consistent. For billions of years, Earth has been slowing down. The rate varies depending on continental configurations, ocean geometry, ice coverage, all factors that affect how efficiently tidal friction operates. But the overall direction is unmistakable. Days get longer, the moon drifts away. The ancient dance initiated by the collision that formed the moon continues slowly winding down. From this perspective, from the vantage point of deep time, the current acceleration is a blip. A tiny fluctuation on a timescale measured in milliseconds over years, set against a background of massive change measured in hours over hundreds of millions of years. But here's what makes it significant: the rate. Yes, the change is small in absolute terms, but it's happening fast by geological standards. Changes that used to take thousands or millions of years are now occurring over decades. This isn't unprecedented. Earth's rotation has experienced rapid changes before usually associated with major geological events. Large earthquakes can measurably change the day length within minutes. The 2011 earthquake off the coast of Japan, one of the most powerful ever recorded, shortened the day by 1.8 microseconds and shifted Earth's figure axis by about 6.5 inches. But those are singular events. Sudden jolts followed by relaxation back to baseline. What we're seeing now is a sustained trend, multiple years of consistent acceleration. That's unusual enough to warrant attention, especially because it's happening at a time when human activity is also redistributing mass on the planet at unprecedented rates. Which brings us to something most people never consider. We might be part of the equation. The numbers are staggering when you actually examine them. Since the beginning of the 20th century, humans have extracted approximately 2.3 trillion gallons of groundwater from aquifers around the world. Not for a single purpose. For agriculture, for drinking water, for industry, for cooling power plants, for fracking operations. That water, which had been stored underground sometimes for thousands of years, was pumped to the surface and used. Some of it soaked back into the ground. Much of it didn't. It evaporated into the atmosphere. It flowed into rivers and eventually reached the ocean. Mass that had been stored inland, often at mid-latitudes, was redistributed to the ocean, which is predominantly at the equator relative to the total water volume. A study published in 2023 calculated the effect of this groundwater depletion on Earth's rotation axis. The result, the planet's rotational pole drifted approximately 31 inches eastward between 1993 and 2010, partly attributable to groundwater redistribution. 31 inches, not much on a planetary scale, but measurable, real, caused by human activity. This isn't theory, this isn't speculation, this is measured, verified, peer-reviewed science. For 4.5 billion years, only natural forces affected Earth's rotation. The core, the ice, the moon, asteroids. Now, for the first time in the planet's history, one species, us, has joined that list. Measurably, quantitatively, with instruments precise enough to detect our contribution. And it doesn't stop with groundwater. Humans have built massive reservoirs. The Three Gorges Dam in China alone holds back 42 billion tons of water. Thousands of other dams around the world collectively hold back trillions of gallons, storing water that would otherwise flow to the ocean. This has the opposite effect of groundwater depletion. Keeping water inland, often at higher latitudes, slows rotation slightly. The net effect of all human water management is small compared to natural forces like ice melt or atmospheric circulation. But it's not zero. We didn't mean to affect rotation. Nobody set out to change how fast Earth spins. But when you move trillions of tons of water from one place to another, physics doesn't care about intent. The consequences follow regardless. We are no longer observers, Elkins Tanton says quietly. We are participants, part of the system we're trying to understand. This is the new reality, a world where human activity operates at scales that affect fundamental planetary processes. And the rotation measurements prove it. They're not just interesting science, they're evidence. Quantitative, precise evidence that we've become a geological force. This is where Dr. Benjamin Folks enters the story. At 58, Folks is British Oxford educated and has spent the majority of his career studying something that sounds almost whimsical: wobbles, specifically the Chandler wobble. Named after American astronomer Seth Carlo Chandler, who discovered it in 1891, the Chandler wobble is a small, irregular oscillation in Earth's rotation axis. Imagine Earth spinning like a sump, but instead of the axis staying perfectly still, it traces a small circle about 30 feet in diameter over a period of roughly 433 days. 30 feet might not sound like much on a planet 8,000 miles in diameter. And it's not in terms of physical displacement, but it's measurable, detectable with precision instruments, and it reveals something important about how Earth's mass is distributed. The wobble exists because Earth isn't a perfect sphere. Folks explains, speaking from his office in Oxford via video call. His voice carries the measured precision of someone who thinks carefully before speaking. It's slightly flattened at the poles bulging at the equator, and the mass inside isn't distributed perfectly evenly. There are denser regions and less dense regions, mountains and trenches, continents and oceans. All of this asymmetry means the rotation axis doesn't align exactly with the axis of maximum moment of inertia. So the planet wobbles as it spins, trying to find equilibrium. For most of the 20th century, the Chandler Wobble was stable. Predictable, it completed its 433-day cycle and repeated over and over with only minor variations. Then around the year 2000, something strange happened. The wobble nearly stopped. For several years, the oscillation dampened significantly. The circle the pole was tracing became much smaller. Some researchers worried it might disappear entirely. Then it resumed, but changed. The direction shifted, the amplitude varied, and by the 2020s, data from GPS satellites and very long baseline interferometry radio telescopes, separated by thousands of miles, observing distant quasars to measure Earth's orientation, with extraordinary precision, showed that the wobble had entered a new phase. The pole was drifting eastward, not quickly, about 4 inches per year, but consistently, and the suspected causes were mass redistribution from ice melt and groundwater depletion. When you remove mass from one location and add it to another, you change where the planet's center of mass is located, Folks explains, and the rotation axis has to respond to that change. Think of it like balancing a spinning plate on a stick. If you add a small weight to one side of the plate, the whole balance shifts. The plate might wobble differently. It might tilt slightly. The rotation changes. That's what's happening to Earth. The ice sheets are the most obvious example. Folks continues, Greenland alone has lost massive amounts of ice. That's mass that was sitting at high latitude close to the rotation axis. When it melts and flows into the ocean, it redistributes toward the equator. Antarctica is losing mass too, though the picture there is more complex. Parts of the West Antarctic ice sheet are losing ice rapidly. East Antarctica has been more stable, but even there we're seeing concerning signs. All of this changes the wobble, and the wobble in turn affects rotation speed through feedback mechanisms scientists are still working to fully understand. There's a concept in physics called coupling. It describes how different parts of a system interact with each other. In Earth's case, everything is coupled to everything else. The wobble affects how mass is distributed at the surface. Mass distribution affects the core mantle coupling. Core mantle coupling affects the magnetic field. The magnetic field affects atmospheric circulation through mechanisms that are only partially understood. Atmospheric circulation affects ocean currents. Ocean currents affect ice melt. It's not a chain, it's a web. And tugging on any strand sends ripples through the entire structure. What makes the current situation unusual, Folks says, is that we're tugging on multiple strands simultaneously. Ice melt, groundwater extraction, atmospheric changes from climate warming. These are all happening at once, all feeding into the system together. In the past, when Earth's rotation changed significantly, it was usually due to one dominant factor: an ice age ending, a major volcanic eruption redistributing ash, a massive earthquake. Now we have multiple forcing factors all operating on similar timescales, all interacting in ways that make prediction extremely difficult. He pulls up a graph showing Earth's rotation rate from 1960 to 2024. The line is jagged, full of short-term variations, daily, seasonal, year-to-year fluctuations. But the overall trend is clear. From 1960 to about 2020, gradually slowing with periodic leap. Seconds added to compensate. From 2020 onward, accelerating with the possibility of a negative leap second needed for the first time in history. The shift is real, Folks says. The question is whether it's a temporary fluctuation or the beginning of a longer-term trend. And to answer that, we need to understand not just what's happening at the surface, but what's happening in the ocean. Because the ocean is doing something nobody predicted. The ocean doesn't sit still. Most people think of the ocean as a relatively static thing. Water filling a basin, sloshing around with tides and storms, but fundamentally just sitting there. This couldn't be more wrong. The ocean is in constant motion, not just at the surface where wind-driven currents and waves are obvious, but throughout its entire depth, from the sun-warmed surface, waters down to the freezing abyssal plains 3 miles below. This motion is organized, structured, driven by differences in temperature and salinity that create density gradients, which in turn drive enormous circulation patterns that span ocean basins and connect all the world's oceans into a single global conveyor belt. The Atlantic meridional overturning circulation is perhaps the most famous of these systems. Warm, salty water flows northward along the surface of the Atlantic, carrying heat from the tropics toward Europe. As this water reaches the cold regions near Greenland and Iceland, it cools, becomes denser, and sinks. This cold, dense water then flows southward along the ocean floor, eventually reaching Antarctica, where it mixes with circumpolar currents and slowly makes its way into the Pacific and Indian Oceans. The entire cycle takes roughly 1,000 years for a single water mass to complete. This circulation system is crucial for climate. It's why Europe is much warmer than regions at similar latitudes in Canada or Russia. It's why certain marine ecosystems thrive. It's part of how heat energy is distributed around the planet, and it's slowing down. Measurements from ocean buoy satellites measuring sea surface height and deep ocean sensors show that the Atlantic overturning circulation has weakened by about 15% over the past century. Some studies suggest it's at its weakest point in over 1,000 years. The cause is partially understood. Melting ice from Greenland adds fresh water to the North Atlantic. Fresh water is less dense than salt water, so it doesn't sink as readily. This disrupts the sinking phase of the circulation, weakening the entire system. But there's another factor that most people never consider. Earth's rotation affects ocean currents, specifically through the Coriolis effect. When something moves across the surface of a rotating planet, it appears to deflect. In the northern hemisphere, moving objects curve to the right. In the southern hemisphere, to the left. This isn't because any force is pushing sideways. It's because the surface is rotating beneath the moving object. The faster Earth rotates, the stronger the Coriolis effect. The slower the rotation, the weaker the effect. And because ocean currents are driven in part by the Coriolis effect, it's what causes the large gyres in each ocean basin to rotate. The direction they do changes in rotation speed can theoretically affect ocean circulation. The effect is small, much smaller than the influence of wind or temperature gradients. But over decades or centuries, small effects accumulate. Some researchers studying the slowdown of the Atlantic circulation have begun asking whether changes in Earth's rotation might be a contributing factor. The honest answer is we don't know for certain. The rotation changes are small and the ocean circulation changes are driven primarily by other factors. Ice melt, warming temperatures, changing wind patterns. Separating out the rotation effect from everything else is extraordinarily difficult. But the question illustrates something important. The systems are coupled. Everything affects everything else. And the more we learn about these connections, the more complex the picture becomes. But there's one event that brought all of this into sharp focus. Something that happened in Antarctica in 2022 that made glaciologists around the world recalculate their assumptions about what was possible. In March 2022, a heat wave struck Antarctica. Not a metaphorical heat wave. An actual measured temperature spike. Temperatures in some regions rose 70 degrees Fahrenheit above normal. In one location, the temperature reached 10 degrees Fahrenheit in Antarctica in autumn, heading into winter. This was unprecedented in the modern observational record, and it had consequences. The Conger Ice Shelf, a floating platform of ice roughly 460 square miles in area, about the size of Los Angeles, disintegrated in a matter of days. Satellite images showed it fracturing, breaking apart, melting from the surface and bottom simultaneously. Within a week, it was gone. An ice structure that had existed for thousands of years vanished. This was the largest ice shelf collapse ever recorded in East Antarctica, and it terrified glaciologists. For decades, scientists had focused their concern on West Antarctica, where ice sits on bedrock that's below sea level and therefore vulnerable to warming ocean water flowing underneath. East Antarctica was considered the fortress. Too cold, too thick, too stable to worry about in the near term. The Conger collapse suggested that assumption might be wrong. Ice shelves are crucial because they act as buttresses holding back the glaciers behind them. Think of a dam. The dam itself isn't the water, but remove the dam and the water flows freely. Ice shelves work similarly. They don't contribute to sea level rise themselves, they're already floating. But they keep the land-based ice behind them from flowing rapidly into the ocean. When an ice shelf collapses, the restraint is removed. Subsequent research using ice-penetrating radar instruments that send radio waves through ice and measure the reflections from the bedrock below revealed something even more concerning. Beneath parts of the East Antarctic ice sheet, researchers found a network of valleys and channels carved into the bedrock. Some of these channels extend below sea level. Some connect to the ocean through subglacial pathways. This means warm ocean water could potentially reach the base of East Antarctic glaciers. Not just at the edges where ice meets sea, but underneath through hidden channels melting from below. If this happens, if warm water finds these pathways and begins melting ice from underneath the collapse, could accelerate far faster than models predict. And the implications for rotation are significant. The East Antarctic ice sheet contains about 52 million cubic kilometers of ice. If it melted completely, which isn't happening soon, but which could happen over centuries if warming continues, sea levels would rise by approximately 170 feet. Every coastal city on Earth would be underwater. Bangladesh, the Netherlands, Florida, most of the Amazon basin gone. But beyond the obvious catastrophe of sea level rise, there's the rotation effect. All that ice sitting at the pole as close to the rotation axis as you can get on Earth's surface would melt and flow into the ocean. Mass redistribution on a scale that would dwarf anything in human history. The planet's moment of inertia would change dramatically. Rotation speed would respond. Days would get measurably longer. The Chandler wobble would shift significantly. The rotation axis itself could drift by feet or even yards. This is long-term. Century scale. Not an immediate concern for anyone alive today, but it illustrates the stakes of what's happening right now. The ice sheets aren't just climate change indicators. They're active participants in planetary dynamics. Massive repositories of frozen water that, when released, alter the fundamental physics of how Earth spins. And we're in the early stages of that release. The question is, what do we do with this knowledge? How do we navigate a future where the very rhythm of day and night is changing? There's a particular kind of monitoring station that most people have never heard of. They're called VLBI stations, very long baseline interferometry. The name is technical and uninformative unless you know what it means. What it means is this: we've built a network of radio telescopes around the world, in Hawaii, Chile, Germany, Australia, Alaska, dozens of locations, and we point them all at the same thing. Not planets, not stars, quasars. Quasars are among the most distant objects in the universe. Supermassive black holes at the centers of ancient galaxies billions of light years away so far that their light has been traveling toward us for most of the universe's existence. And because they're so absurdly far away, they appear essentially motionless from Earth's perspective. They're fixed points, cosmic reference markers. When multiple radio telescopes observe the same quasar simultaneously, tiny differences in when the signal arrives at each telescope reveal information about Earth's orientation. The planet's rotation, the wobble, the precession, the precision is staggering. VLBI measurements can detect changes in Earth's rotation to within 0.1 milliseconds. They can track the position of the rotation axis to within a few millimeters. They can measure the planet's orientation in space more accurately than any other method ever devised. And they've been doing this continuously since the 1970s. Dr. Margaret Thornwell has spent 30 years working with this data, now 65, having devoted the majority of her career to the precise measurement of Earth's orientation. She works at the National Institute of Standards and Technology in Boulder, Colorado, the same facility that houses the atomic clocks that define the second itself. Her office overlooks the mountains. On clear days, she can see the continental divide from her window, but she rarely looks at the mountains. Her attention is on screens displaying numbers, coordinates, measurements of how the planet beneath her is positioned relative to distant quasars that will outlast humanity by billions of years. Most people don't think about Earth's orientation, she says. Her voice is calm, measured the voice of someone who has spent decades watching numbers change by fractions of millimeters. They assume the planet just spins smoothly, axis pointed at Polaris, everything constant. But that's not reality. She pulls up a visualization. It shows Earth's rotation axis over the past 50 years, traced as a line wandering across a map of the Arctic. The line doesn't go straight, it wanders, drifts, spirals in small loops. This is the Chandler wobble combined with annual variations in longer-term drift, she explains. Every force acting on the planet shows up in this motion: earthquakes, ice melt, ocean circulation changes, atmospheric momentum transfer, groundwater extraction. We can see all of it if you know how to read the data. And the data over the past few years has been telling a clear story. Earth's rotation is accelerating. The trend is unmistakable, Thornwell says. Day length has been decreasing. Not smoothly, there are fluctuations, reversals, short-term variations driven by weather and ocean dynamics. But the overall direction is clear. For the first time in the modern era of precision timekeeping, we've had serious discussions about implementing a negative leap second. She pauses, letting that sink in. That might not sound dramatic, it's just 1 second. But implementing it would be extraordinarily complex. Every computer system, every satellite, every GPS receiver, they'd all have to handle time moving backward by 1 second. Most software has never been tested for that. We don't know what would break. The potential consequences range from annoying to catastrophic. At the minor end, some websites might crash. Some timestamp-dependent services might glitch temporarily. At the serious end, GPS satellites could provide incorrect position data. Financial trading systems could malfunction. Power grids synchronized across continents could experience cascading failures. GPS might not seem like a critical technology to most people. It's convenient, certainly. Useful for navigation, for finding restaurants, for tracking your morning run. But GPS is infrastructure now. Foundational infrastructure that an enormous amount of modern civilization depends on without realizing it. Every cell phone tower uses GPS to synchronize its timing. When you make a call, the signal hops between towers with nanosecond precision. That precision requires knowing exactly what time it is synchronized across the entire network. The financial system uses GPS timing. Stock trades are timestamped to microseconds to determine the order they occurred in. High-frequency trading algorithms executing thousands of trades per second depend on that timing being accurate and consistent. The power grid uses GPS. Generators across a continent need to be perfectly synchronized, their alternating current waveforms aligned to within microseconds, or the grid becomes unstable. GPS provides that synchronization. Precision agriculture uses GPS. Autonomous tractors plant seeds in perfectly straight rows guided by satellite positioning accurate to within inches. All of this depends on knowing with extraordinary precision exactly where Earth is in its rotation at any given moment. And that depends on accurate models of rotation speed. When rotation changes, the models have to be updated. Earth orientation parameters. The technical name for the data describing how the planet is positioned and how fast it's spinning are published regularly by the International Earth Rotation and Reference System Service. GPS satellites download these updates and adjust their calculations accordingly. Usually this happens smoothly. Small corrections frequently updated, keeping everything synchronized. But a negative leap second would be different. This is why the International Telecommunication Union voted in 2022 to abolish the leap second entirely by 2035, Thornwell explains. Instead of keeping atomic time synchronized with Earth's rotation at the 1-second level, they'll let the two timescales drift apart. Corrections will still happen eventually, but over much longer intervals. Centuries, perhaps. This is a profound decision, though most people will never realize it. For the first time in human history, we're decoupling our clocks from the planet's rotation. Time as we measure it will no longer be directly tied to the astronomical reality of day and night. Instead, it will be defined purely by the vibrations of cesium atoms. Some people see this as a defeat, Thornwell admits, giving up on keeping human time synchronized with planetary time. But I see it differently. We're acknowledging reality. Earth's rotation is variable, chaotic, on short timescales influenced by dozens of factors we're still working to fully understand. Trying to keep our clocks locked to it second by second was always going to become untenable as our need for precision increased. So we're choosing precision over astronomical alignment. That's not a failure, it's maturity. But it also represents something else, an acknowledgement that the forces controlling Earth's rotation are beyond our control. We can measure them, we can understand them, but we can't stop them. The core will do what it does. The ice will melt or accumulate according to climate. The atmosphere will circulate. The moon will drift away. And Earth will spin faster or slower in response. All we can do is watch, measure, try to understand, and adapt our systems to reality rather than expecting reality to conform to our systems. But beyond the technical challenges, beyond the engineering questions of how to handle a negative leap second, or whether to abolish leap seconds entirely, there's a larger question. What do these rotation changes tell us about the planet's future? Dr. Benjamin Folks has been modeling this question for years. Using data from ice sheet monitoring, ocean current measurements, atmospheric circulation models, and core dynamics simulations, he's built what he calls an integrated rotation forecast model. It doesn't predict exactly what rotation will be at any specific future date. The system is too chaotic for that, but it maps the probable trajectories based on different assumptions about the variables we can't measure directly. Think of it like weather forecasting, he explains, video calling from Oxford. Outside his window, rain streaks the glass England in February. We can't tell you whether it will rain on June 15th, 2030, but we can say if current trends continue, June rainfall in England will likely increase by 10 to 15% over the next 2 decades. Same principle here. We can't tell you the exact length of a day in 2050, but we can give you the range of possibilities and their probabilities. His model's central projection rotation will continue accelerating until approximately 2035, at which point ice melt effects will begin to dominate and days will start getting longer again. By 2,100 days could be 2 to 3 milliseconds longer than they are now, assuming moderate ice loss scenarios. In more extreme scenarios, if the West Antarctic ice sheet experiences rapid collapse, if Greenland melt accelerates beyond current projections, days could be 8 to 10 milliseconds longer by century's end. That sounds small, folks says, and in absolute terms it is. 10 milliseconds won't affect anyone's daily life. You'll never notice it. But it represents an enormous mass redistribution. Trillions of tons of ice flowing into the ocean, sea level rise measured in feet or meters, coastlines fundamentally reshaped. The rotation change isn't the problem, it's the symptom. It's the planetary scale manifestation of changes that will reshape human civilization. He pauses, choosing his words carefully. What I find profound is that we can measure it. We can watch the planet redistribute its mass and see the effect in rotation speed. We can literally observe the physics of a changing world in real time. Previous generations couldn't do that. They experienced climate change, ice ages, warm periods, all of it, but they couldn't measure the planetary dynamics behind it. We do, and that gives us something they didn't have: foresight. Foresight doesn't mean certainty. The models have uncertainties. The future has variables we can't predict. Political choices, technological breakthroughs, unforeseen tipping points in the climate system. But foresight means we're not blind. We can see the major forces at work. We can understand the physics. We can map the terrain of possibilities. And we can prepare. The abolition of leap seconds by 2035 is one form of preparation. Adapting our timekeeping systems to reality rather than expecting reality to conform to our systems. But there are others. GPS systems are being upgraded. Next-generation satellites with more sophisticated timing systems, better able to handle rotation variability. Ground stations with more frequent updates to Earth orientation parameters. Climate models are incorporating rotation effects. Not because rotation changes climate, it doesn't, at least not at the scales we're discussing. But because rotation is an indicator, a metric that integrates multiple aspects of the Earth system into a single measurable number. When you see rotation changing, you know mass is redistributing. You know the climate system is active. You know forces are at work. And increasingly, scientists are using rotation data as a check on other measurements. If satellite data shows ice loss of a certain magnitude, rotation should change by a calculable amount. If it doesn't, either the ice measurement is wrong or there's another mass redistribution we haven't accounted for. Rotation is becoming a diagnostic tool, Folkus says, a way to verify that we're understanding the whole system correctly. It's like checking your work in mathematics. If you add up all the forces and the rotation change doesn't match what you predict, you know you've missed something. This is how science advances. Not just by measuring more things, but by finding connections between measurements, by using different observations to verify each other. And rotation touches everything: core, mantle, ocean, atmosphere, ice, even human activity. It's the ultimate integrator, the one number that reflects the collective behavior of every moving part of the planet. There's a larger perspective worth considering. Earth has been rotating for 4.5 billion years, through ice ages of squeeze and hothouse climates, through asteroid impacts and volcanic cataclysms, through the rise of continents and the opening and closing of ocean basins. Through all of it, the planet has kept spinning, sometimes faster, sometimes slower, but always spinning. The moon has been pulling on the tides for all that time, slowly stealing rotational energy, gradually lengthening the day. When the first single-celled organisms appeared in Earth's oceans, a day was perhaps 16 hours long. By the time of the dinosaurs, it was 23 hours. Now it's 24. Billions of years from now, if Earth survives the sun's eventual expansion into a red giant, the day will be much longer still. Eventually, the planet might become tidally locked to the moon, rotating once per orbit, always showing the same face to the lunar surface, the way the moon currently shows the same face to us. One side in permanent daylight, the other in permanent darkness. That's the end point of the tidal breaking process, not a destination we'll reach, not something anyone alive today or their descendants for millions of generations needs to worry about, but it's the direction the system is heading, slowly, inexorably. The current acceleration, the few milliseconds per year we're measuring right now, is a tiny fluctuation on that billion-year trajectory, a ripple on an ocean. This perspective doesn't make the current changes unimportant. They matter for GPS, for timekeeping, for understanding the climate system. But it does put them in context. We're living through a moment of rapid change by human standards. Ice melting faster than it has in thousands of years. Climate warming at rates not seen in millions of years. Human activity reshaping the planet at scales that register in geological records. All of this is unprecedented in human history. But in Earth's history, it's happened before. Not exactly the same way. Each period of rapid change has its own character. But the planet has been through massive reorganizations before. Ice ages, greenhouse periods, the great oxygenation event when photosynthetic organisms first pumped oxygen into the atmosphere, fundamentally transforming the planet's chemistry. Earth adapts, life adapts, systems reorganize. The question isn't whether the planet will survive. It will. Earth is resilient on timescales that dwarf human civilization. The question is whether we'll navigate the transition wisely. Dr. Margaret Thornwell stands in the basement of the NIST facility in Boulder surrounded by atomic clocks. These are not the sleek devices you might imagine. They're racks of electronics, optical tables with lasers and mirrors, magnetic shielding, temperature control systems. The machinery required to measure time with precision beyond anything imaginable a century ago. The temperature in the room is controlled to within a tenth of a degree. The magnetic field is shielded to prevent interference. The lasers that probe the cesium atoms are stabilized against vibrations that would be invisible to human senses. All of this precision for one purpose: to count atomic vibrations with perfect accuracy. And using this precision, we can measure Earth's rotation to fractions of milliseconds. We can track changes that occur over days, months, years. We can watch the planet breathe. This is what I think about, Thornwell says, her voice quiet in the temperature-controlled room. We've built machines that let us see things no human in history could see, changes happening so slowly they'd be invisible without atomic-level precision. And now we see them, every day, every measurement. The planet is changing, its rotation, its climate, its ice sheets, everything interconnected, everything affecting everything else. And we're part of it, not separate from it, not observers standing outside the system. We're in it. Our actions affect the rotation speed measurably. She walks to a monitor displaying real-time data from BICLBI stations around the world. Green dots marking operational telescopes. Lines connecting them to the quasars they're observing. Numbers streaming past coordinates, measurements, uncertainties. But it's also triumph, she continues, because we can measure it, we can understand it. We're not stumbling blind into the future. We know what's happening. We know why. We know the major forces at play. We don't know everything. We can't predict exactly what will happen, but we know enough. Enough to adapt, enough to prepare, enough to make informed choices. She touches the screen lightly as if feeling the data flowing through it. Louis Essen spent years building the first atomic clock. John Vidal spent decades analyzing seismic data before he could say with confidence what the inner core is doing. Duncan Agnew devoted 40 years to watching the wobble. Patience, that's the lesson. Not everything happens quickly. Not everything should. But if you measure carefully, if you watch patiently, if you build on what others have learned, eventually you understand. And understanding is victory. In Boulder, Colorado, the atomic clocks continue their endless counting. 9,192,631,770 vibrations per second. Never varying, never stopping. In Iceland, seismometers record earthquake waves traveling through the planet's interior, carrying information from depths no human will ever visit. In Hawaii, Chile, Germany, Australia, radio telescopes point at quasars billions of light years away, measuring how Earth rotates beneath them. In Antarctica, sensors buried in the ice track temperature, thickness, flow rate, the slow dissolution of ancient frozen water into the warming ocean. In laboratories around the world, scientists analyze data, build models, compare observations, refine theories, and slowly, patiently, the picture becomes clearer. We know Earth is spinning faster right now than it has in 50 years. We know the major forces causing this. The inner core's change rotation. Ice melt, paradoxically overpowered by other factors, atmospheric momentum, transfer the moon's endless tidal pull. We know humans have joined this list of forces, not intentionally, but measurably. We know the current acceleration is likely temporary, that ice melt effects will eventually dominate, that days will start getting longer again, probably within our lifetimes. We know there are still unknowns, uncertainties, questions we can't yet answer, but we also know we're asking the right questions, building the right instruments, making the right measurements. And that knowledge, incomplete though it is, represents something profound. For 4.5 billion years, Earth has been spinning, changing, evolving. And for 4,499,999,930 of those years, no one was watching, no one was measuring, no one was understanding. But now we are. We've built machines that can count atomic vibrations with perfect precision. We've built telescopes that can measure our orientation by observing the edge of the universe. We've built satellites that can weigh ice sheets from space. We've done the mathematics. We've developed the models. We've collected the data. And what we've learned is this: the planet is not static, it's dynamic, constantly changing, constantly responding to forces both internal and external. And we're part of that now. Not just observers, participants. Our choices matter. Our actions have consequences at scales that ripple through the entire Earth system. But we're not helpless. We're not blind. We can measure, we can understand, we can adapt. This is the triumph, not that we've solved everything, not that we know the future with certainty, but that we've looked at a problem that spans from the center of the Earth to the edge of space, from milliseconds to billions of years, from the atomic scale to the planetary scale. And we've made sense of it. We've built a coherent picture. Incomplete, yes. Still developing, yes. But coherent. We know what forces affect rotation. We can measure their contributions. We can make projections about the future based on physics and observation rather than guesswork. And in the contest between cosmic forces and human understanding, between a planet that's been spinning for 4.5 billion years and the minds trying to comprehend it, understanding wins. Not completely, not perfectly, but genuinely. We know things our ancestors couldn't have known. We see things they couldn't have seen. And we'll pass that knowledge forward to the next generation of scientists who will build better instruments, collect more data, refine the models. To the engineers who will design systems that work with rotation variability rather than fighting it. To the people who will make choices about climate and water and land use, hopefully informed by understanding of planetary scale consequences. The rotation will continue. The planet will keep spinning. The forces will keep acting. But we'll be watching, measuring, understanding. And that's enough. Not to control the planet. We can't do that and shouldn't try. But to navigate the changes wisely. To adapt. To continue the work of understanding, which is in the end what we do best. Not as individuals, as a species, as a civilization built on accumulated knowledge passed down through generations. Each one adding to what came before. Each one seeing a little farther. Each one understanding a little more. Right now, as you finish hearing these words, you are still spinning, 1,000 miles per hour. The same speed you were spinning when we began. But now you know something you didn't know before. You know that speed is not constant, that it changes, that it's changing right now measurably in response to forces operating at every scale from the atomic to the cosmic. You know that liquid iron is churning thousands of miles beneath your feet, that ice is melting at the poles, that the atmosphere is transferring momentum, that the moon is pulling on the tides and drifting slowly away. You know that these forces are real, measured, understood at least partially. You know that humans have become part of this system, that our actions aggregated across billions of people move enough mass to affect how the planet spins. You know that scientists have spent decades, careers, lifetimes patiently building the instruments and collecting the data to make all of this visible. And you know that the work continues. Every day, Margaret Thornwell downloads new Earth orientation parameters. The numbers stream across her screen. Rotation rates slightly different from yesterday. She uploads the data to the international database. Somewhere a GPS satellite adjusts its calculations. Somewhere a scientist in Tokyo notices the change and adds it to their model. Somewhere a student reads about atomic clocks and wonders what else we might learn to measure. The work continues. The measurements continue. The understanding grows, and the planet spins, day after day after day, sometimes faster, sometimes slower, but always spinning. And now finally, after 4.5 billion years of blind rotation, we're watching, we're measuring, we're understanding the iron core and the ice sheets, the atmosphere and the moon, the equations and the measurements, all of it coming together into comprehension, all of it showing us who we are and where we stand, spinning. Part of a system that we're only beginning to fully grasp, but grasping it, day by day, measurement by measurement, understanding growing, and in that growing understanding, in that patient accumulation of knowledge, in that triumph of human curiosity and precision and persistence, there is hope. Not that everything will be easy, not that the future is certain, but that we're facing it with open eyes. with working instruments, with minds that question and measure and calculate and understand. The planet spins, we spin with it, and now at last we know why, we know how, we know what forces are at work, we know what they mean. This is science, not magic, not speculation, not guesswork. Patient observation, careful measurement, rigorous analysis, building on what came before, testing hypotheses, refining theories, year after year after year, until the picture emerges, until the mystery yields to understanding, until the question is answered, not perfectly, not completely, but well enough to navigate forward, well enough to adapt, well enough to continue. This is what we've achieved. This is what Essen and Vidali and Agnew and Dunbarry and Elkins Tanton and Folks and Thornwell and thousands of other scientists whose names we haven't mentioned have given us. Not just data, not just measurements, understanding of our planet, of ourselves, of the deep connections between human action and planetary response, of the forces that govern our world. The planet spins, and we understand why. That's the triumph, that's the victory, that's the story.